Hello. Can we start? Yeah. Yeah. Okay. Okay, good afternoon to all. Thanks to be there late afternoon for this last lecture of the day. Thanks for Benoit for the invitation. So I will focus my speech on how to build a sustainable precast segment with fiber reinforced concrete. So I'm Benoit de Rivaz, working for Bekaert. I'm coming from France. Agenda will be first few words of introduction, focus on structural requirements, low carbon requirements, sustainable development, and a few words of conclusion. So I'm working for Bekaert. Bekaert is the world's largest independent producer of steel wire, product and solution, serving customers from a very wide range of industry around the world in 120 countries, and operating at a global manufacturing platform with almost 30,000 employees worldwide. Bekaert has a strong presence in diverse industry sectors as the automotive, equipment, basic material, consumer goods, agriculture, and construction. Just to give some idea of the key product, about 30% of all tires around the world are reinforced with Bekaert tire cord. Every year, 1 billion of bottles of champagne wines are opening via the muslin made by Bekaert steel wire. And every year, 10 million cubic meters of concrete is being reinforced with Dramix steel fiber invented by Bekaert. Indeed, we are involved in a fiber reinforced concrete for many years, 40 years, and we promote a smart, sustainable fiber reinforced solution for every need. Every need means easy dosing, easy mixing, high performance, extreme network, and green durability. So our products are used in the main tunneling application as a spray concrete temporary lining, as well as for spray concrete permanent lining, also in cast in place, and also in precast segment, which is the focus of today. For all these applications, we have different type of product with different geometry, different line, different property to meet the specific concrete recipe, the specific application, and the specific performance requirements. We have the Dramix 3D, 4D, 5D according to all these requirements. We use worldwide more and more mechanized excavation using TBM, tunneling boring machine. This technology is improving years after years, and you can visit the big TBM booth, and you can see how this machine can lead all type of geology, different ground conditions, how this machine can adapt to different geometry, diameter, and we see that the TBM are used in all industry, from water tunnel, metro tunnel, highway, road tunnel. In metro is the main method of excavation due to the good control of the settlement. So in the meantime, we use more and more fiber reinforced concrete in precast segment. So today is no more an exotic solution, is a standard solution, which is supported by a clear state-of-the-art which is very well summarized in the Fibre Bulletin 83 that I will introduce later. So what this state-of-the-art say? Durability advantage, final stage. Cracking control during the construction phase, which is very important. Higher impact resistance. Boosting the production process. Of course, reduction of costs, cost saving, and sustainability advantage, which is the key words today, as we are looking for low carbon solution with the lower embodied footprint. So we are, I think, the leader in underground precast solution with more than 200 projects worldwide the last 30 years. Less steel to save steel and CO2 less emission. Voilà. And this project has been done in a very worldwide in very different projects. So good to mention here that the first project was in 90s in Munich. It was the Munich water tunnel in Germany. Contractor was Binfinger. Since, just to mention a few big breakthrough, certainly was in UK with the CTRL project. The owner of this project was the Eurotunnel. and from that period, we can say that UK is really moving to fiber reinforced concrete, as 100% of the precast segment are reinforced with steel fiber. Then this application was expanding worldwide with projects in Singapore, in India, in Australia, in US. The Lee Tunnel in 2004 was awarded as the concrete project of the year by the Concrete Society. And since 2016, we have a lot of new guidelines. So the application is supported by international guidelines to help to consolidate the state-of-the-art and to facilitate the use by the designer and the contractor. The last big project was also in Grand Paris recently. It's a big ring around Paris, 200 kilometers, and the main part is built with fiber reinforced concrete. So it's a long history already, and this state-of-the-art, as I tell you, is very well consolidated in many documents. Just to keep in mind, the main difficulty with precast segment when we use traditional reinforcement is the spalling bursting effect. This could appear during in-place force due to the compression in the ring, and mainly during the installation. When you install the segment, you have to push with the jack, and you create a very high concentrate load that could lead to this spalling effect. Top of that, due to the minimum cover you need for durability with rebars, plus the edge of the segment, you have a very brittle part with no reinforcement. So to solve this issue at the beginning, it was the main reason to use a fiber reinforced concrete, because you have fiber in all directions. This spalling effect was a problem of durability. You have to repair. How long will you guarantee this repair? It was always a key question. So fiber, as you see, it's 3D in all directions. You have fiber, and you have fiber close to the surface to control this risk of spalling. This is a feedback from the CTRL project, 260,000 segments, 1 major repair, which is a very good number. This is a survey from the customer. Well, this is just a few words of introduction saying that this is a standard solution, which is no more an exotic solution with a strong state-of-the-art. When we talk about final lining, the assessment of concrete lining requires the definition of both the sustainability and mechanical index. Structural requirements, structural safety, and sustainability development goes hand to hand. We cannot design once again the second. This is part of the United Nations commitment to move to this long-term development, CO2 saving. And these two requirements today have the same level of importance. And this is I would say, the key reason why there is a new boost also with fiber reinforced concrete. If the initial keyword was ductility, we have seen after that durability was the key booster, and now it's really looking for sustainability, which will help to use this solution more and more in the future. So let's look a few basic principles about the structural requirement. But this is just an overview of the key publication and guideline edited in the recent year. I think the main breakthrough was in 2012, the publication of the model code. The model code is express the design principle, is the standard. Since the model code, many publications specifically focus on precast segment has been produced by different international committee, international tuning association, as the AFTES, the French Tuning Association. Then the ITA, International Tuning Association, published 3 documents from committee ITATEC, from the committee, from the Working Group 2. Working Group 2 is more the 25 years lesson learned with many case studies. The ITATEC document is more focused on design. All these documentation are very complementary. So, and one important document is also the Fibre Bulletin 83, which gives a comprehensive and complete approach on how to design a precast segment. You have also the ACI, American Concrete Institute, saying that, just to show that all international committees provide the same state-of-the-art to promote this solution on the market. So the Fibre Bulletin the model code, so it's published in 2012. It's a pre-normative. You should know that it will be used as a pre-standard for the Eurocode, the new Eurocode 2 that maybe will be published next year. It's proposed operational document for designer. The Fibre Bulletin 83, it's a clear guideline how to characterize fiber reinforced concrete, a clear state-of-the-art, and a clear design rules. It go very much in detail, especially for the precast segment. So I will not go in detail this afternoon because it's not the place to, but you can see in the content that touch every part of the life of the segment from the beginning, how to get the relevant material property, the transition state loading condition, the TBM trust, the final state loading condition, the fire design, the connector, the durability issue, the quality control issue, and the sustainability. This is the first document which introduced some sustainability index and different case study to support also the designer with real example. So it's really the document I encourage to get if you want to get a right guideline and the right design approach for this application. You can download from the Fibre secretary. So a few words about the design flow. All start from the relevant material property, and from that you move to the material behavior with constitutive law, with material safety factor, to the actual load situation, demolding, staking, transport, service to the resisting load. But the first part where we have to focus is to provide a relevant material property, and this is done using a beam test according to the EN 14651. This beam test is a 3-point bending test with notch. This test is introduced in all the guidelines and gives 2 key values for the contractor and the designer. So you have such type of curve. The first part of the curve is the concrete strength itself, and after the crack, you see the behavior of the fiber reinforced concrete. So the second part of the curve is the most important when we are talking about fiber reinforced concrete. And there is 2 criteria. One criteria named FR1, which is the residual strength for a crack move opening displacement of 0.5 millimeter, which is used for service limit state design. And the second criteria named FR3 is the residual strength for 2.5 crack move opening displacement, which is used for ULS, ultimate limit state. Voilà. And this beam test is also used as the reference testing procedure in the model code when you classify your material, as you classify C50, you do a compressive strength to validate your material. If you classify C50 4C for fiber reinforced concrete, that means you need 4 MPa characteristic value FR1, and you can check if you concrete mix you use, the fiber and the dosage that you achieve that. So it's a very structural way to specify and to validate the material property. And the letter C means the ratio between FR1 and FR3. C means this ratio should be 0.9 and 1.1. So just to keep in mind, there is a clear testing method, clear performance class according to model code. So for the designer, it's very easy to specify which material he will need for the project according to the load condition, according to the design principle. This is an example of the material with 40 kg Dramix 4D8060 BG. So you see that after the first crack, you have a hardening post-crack behavior. This is a typical curve we want to achieve, showing that after the first crack, FR1 still increasing and FR3 still increasing. It's a high level of ductility. Voilà. That could be achieved using the right fiber in the right mix design, of course. Fiber reinforced concrete is a composite material, so that's why we need to do this test for each project at early stage in order to allow a mix optimization. So the right dosage, the right fiber could conduct with a high level of performance. For example, here we have a 5E. That means the residual strength, FR1, characteristic value is higher than 5 MPa. Hardening post-crack behavior is very important when we talk about fiber reinforced concrete only. It means hardening behavior in bending at section level on beam test allow immediately cracking control, service limit state, structural utility, ultimate limit state. So this is the key minimum criteria to keep in mind when we want to use fiber reinforced concrete only for precast segments. In practice, the performance class minimum for precast segment today is 4C, which is a way to guarantee this hardening post-crack behavior. From the beam test, we can also do some test scale 1 to validate also the good behavior of your material. Test scale 1 on bending to simulate also this hardening at the real scale and also to monitoring the crack. Another test which is also very important is to simulate the point load test or to simulate the jack force, that we know that the high pressure during the installation is very often the most critical load case that we can approach by design, but we can approach also by design by test. And this test setup allows to monitoring very well the crack opening. And from this test, we have seen that when we unload, the maximum crack opening was 0.05 millimeter, which is very low and a very good result. Durability. Well, it's a topic by itself, but most of the projects are designed with 100 years, 120 years design life. Cracking control is key. That's why we use steel fiber. If we don't go too much in detail on the state of the art, but the chapter 8 of the Fibre 83 provide this detailed state of the art, saying best for the cracking concrete and best for the uncracking concrete as well. So there is a strong consensus today to say in terms of durability, fiber reinforced concrete is the way to go. The point of discussion, of dissensus in the international scientific community is about the maximum crack opening according to the class of exposure. More or less today is 0.2 millimeters. So durability, a key driver for precast segment and the main reason we use today fiber reinforced concrete. Some evolution in the segment, we see that the compressive strength increase year after year because there is a high demand for early demolding. Early demolding could lead at 28 days to very high compressive strength. If it specifies a C40 for the structural requirement, due to the early demolding requirement, we can get a 70 and 80 MPa. That's why we have always to adapt the type of fiber to the concrete recipe. So the quality of dry mix is due to a combination of factors: the wire strength, the wire elongation, the shape, the length, the diameter, the LD ratio. But one point which is important to keep in mind is that the tensile strength of a steel fiber has to increase in parallel with the strength of its anchorage. Only in this way can the fiber resist the force acting upon it. That means you have always to adapt your tensile strength to the quality of your anchorage. That's why we have also always upgrade our product according to this complexity. And today we use mainly a 4D 8060 BGP for precast segment. Why? Because we have a high tensile strength, 2,200 MPa, a very strong anchorage due to the double anchorage with the 4D hook that we can use in a high compressive strength without any risk of snapping. So we can get by this way and guarantee this hardening post-crack behavior. Voilà. So network is key. 40 kg means more than 10 kilometers of wire per cubic meter. And it's also very important. You can get a fantastic fiber, but if you have just one, you have not the network. So you need the right fiber, but the right network. And this right network is also lead to the diameter of the fiber. Voilà. So it's always an optimum between the LD ratio, the tensile strength, and the anchorage. And this optimum today is well known when you know fiber reinforced concrete and how we can achieve that in different mix design. So now let's move to the low carbon requirement, which is the second key major point. I quote Charles Allen, which is a well-known consultant, saying that today concrete is recognized as the second most widely consuming commodity of the planet after water. It also contributes approximately to 8% of the global carbon. And when we go to the tunneling project, it is generally considering that 60 to 70% of the carbon consumption is due to the concrete lining itself. So if we want to decrease the CO2 consumption of the tunneling project, we have really to focus on this optimum tunneling lining approach. That's why today the designer moved to optimize the final lining in order to reduce the CO2 consumption due to the big impact on the whole project. So it's a long way. It's not will be done in one day. I just mentioned the journey we got in Middle East. Middle East, many projects has been done based on the model code and fiber reinforced concrete. Middle East was very interesting because the very aggressive environment, high level of sulfate, high level of chloride. Due to that, and the 120-year design life, the designer at that time was COWI, which was working deeply on this topic, tried to optimize the design to achieve the durability requirement. But doing that, we have seen as well that we can also achieve the sustainability requirements. From the first project with Portland cement and rebar, we moved to project with GBBS, fly ash, and steel fiber. And we can see that there is a big impact in terms of CO2 consumption. If we look, for example, the Copenhagen Metro compared to the Doha Metro, if Doha Metro have just 0.2 tons, Copenhagen is 0.7 tons per cubic meter. So if Doha Metro will be built as traditional, that means 400,000 more CO2 emission. That's a big gap. And this is the main trend today. I think we will not go back to old solution when we see this big impact in CO2. Key message also from this slide, I take this slide from a paper from COWI that you can get also, is a consultant view on service life design. The key message is durability and sustainability goes hand to hand. Voilà. To achieve durability, we move to GBBS and fly ash. Instead of rebar, we add steel fiber, and we get this good results. An example of a recent project is the Grand Paris Express in Paris. Grand Paris is a new ring around Paris, is about 200 kilometers. So it's the new network is the same length as the existing one. And the first lot, the line 16, was built with fiber reinforced concrete only. Owner is Société du Grand Paris, the designer is Aegis, the contractor is Eiffage. Design life 100 years, and this project has been very well documented. We do a big testing program to confirm the solution. The owner was really active also, the Grand Paris, to push for innovative solution, to push for low carbon lining, and to support the idea to use fiber reinforced concrete only instead of rebars. Doing that is about 5,000 tons of steel saved for 10 kilometers of tunnel. On top of that, we can also decrease the thickness of the segment by 2 to 3 centimeters because you don't need this minimum cover for durability that you need for rebars. So altogether, that means 10,000 tons of CO2 are saved on average of 10 kilometers of tunnel compared to rebars. So it's also a good example from a big city, from a big owner, that the market is step by step moving for such a solution. Some innovation. I will go fast in the few minutes we have, just to introduce the ultra-low embodied carbon steel fiber reinforced concrete geopolymer. The EFC, it's concrete technology which has been developed by Wagner Concrete over the past decade. It contains no Portland cement, and the binder content comprise approximately 75% GBBS and 25% fly ash. So Wagner work on this new type of binder, and also you can see the impact is very huge compared to a CM1 800. To the EFC, you go to 120 CO2 content per cubic meter. For this, with this material, different tests has been conducted to the fire test to see how this such concrete behave under the different fire curve. The result was very positive. We do also tests to simulate the residual strength with Dramix. With low dosage of Dramix, we get high AFR1, AFR3 as well. So it's very encouraging. They do also tests on durability to check the chloride ion migration coefficient and to check the chloride ion diffusion coefficient. As well, the results are quite positive and encouraging. We have seen that we can cast this concrete correctly. So the main learning point of this concrete provide excellent long-term durability. Compressive strength, C50 could be achieved easily. Flexural strength are comparable to those with Portland cement. And of course, a reduction of CO2. We, as industry, have to work on this CO2 saving. Today, we have to produce what we call a EPD. It's transparently communicate. It's a way to communicate transparently the key environmental performance indicator of the product itself. It's validated by independent body, and this could be used in different tools as the one-click LCA, which is a free tools to calculate the carbon footprint of your material. And from that, you can simulate different concrete mix, different binder, different type of reinforcement, and you can really do a CO2 consumption. We're still working on new and more green fiber. So it's a no-end process to upgrade our EPD certificate. And this is really a journey where we are deeply involved. Voilà. So, few words of conclusion. Solution for reducing CO2 are more and more important, more and more needful. And we think that in this long process, the fiber reinforced concrete could be helpful and to help designer, contractor to provide optimum design, meeting the structural requirement, and in the meantime, meeting the sustainability development. Thank you very much for your kind attention, and do not hesitate to contact me by email or visit us on the booth C3241. Thank you very much.